Thursday morning near Anchorage, the Earth shifted, magnitude 6, no tsunami, no visible damage. Official reports call it just another Alaska quake. But days before, seismic networks recorded strange, low-frequency tremors no one expected. Scientists are not just unsettled, they are warning this could be the first tremor in a hidden chain. What are researchers seeing beneath Alaska's surface that makes them sound the alarm, and why are bigger risks suddenly on the table? At 8:11 a.m. on November 27, 2025, seismic monitors across Alaska registered a sharp jolt northwest of Anchorage. The U.S. Geological Survey measured the earthquake at magnitude 6.0, placing the epicenter about 37 miles from the city in the Matanuska-Susitna borough. Instruments pinpointed the depth at just over 80 kilometers, deep enough to dampen surface shaking, yet still within reach of communities stretching from Susitna to Anchorage's outskirts. Within minutes, the U.S. Geological Survey issued its official bulletin. The summary was clear: no tsunami warning, no widespread structural damage, no immediate casualties. Anchorage's skyline stood unchanged, and morning routines resumed almost as if nothing had happened. For a region that sits atop one of the world's most active subduction zones, this was, at first glance, just another entry in Alaska's long earthquake catalog. Yet the numbers carried weight. A magnitude 6.0 is not a minor event, especially as the strongest quake recorded in Alaska since 2021. The intermediate depth suggested movement not on a shallow fault, but possibly within the boundary where the Pacific Plate dives beneath North America. This is the same tectonic engine that produced the catastrophic Good Friday quake in 1964 and countless smaller shocks since. Alaska's seismic networks, from USGS to the Alaska Earthquake Center, rely on these bulletins to assess risk in real time. Their initial hazard statement noted the absence of tsunami conditions, a critical reassurance for coastal communities still haunted by past disasters. Early data showed no major interruptions to power, transport, or emergency services. Official response channels remained on standby, and the all-clear for immediate threats came quickly. Still, the event's parameters, magnitude, depth, and location demanded scientific attention. The quake's signature did not fit the pattern of shallow crustal slip. Instead, it hinted at deeper tectonic movements beneath the surface, where stress builds quietly for years or decades. For geologists, these details raised questions that routine bulletins could not answer. The numbers were precise, but the story behind them was far from ordinary. In the weeks before the earthquake, analysts at the Alaska Earthquake Center noticed a subtle but persistent pattern on their waveforms. Low-frequency tremors, often too faint to be felt at the surface, began appearing across several stations northwest of Anchorage. These were not the sharp, abrupt jolts typical of shallow fault ruptures. Instead, the signals stretched out, long, rolling vibrations that sometimes lasted for minutes, blending into the background hum of the subduction zone. Technicians pulled spectrograms from the region's broadband seismometers. On these plots, the tremor swarms stood out as streaks in the 1 to 10 Hz range, distinct from the usual seismic chatter. Over several days, clusters of these low-frequency events pulsed through the crust, sometimes in bursts, sometimes fading for hours before returning. The signals did not match the signature of local quarry blasts or human activity, nor did they line up with the aftershocks of distant quakes. Instead, they hinted at deep, slow movement, possibly fluid migration or the gradual creep of rock along locked sections of the plate boundary. The tremor patterns were clear enough to demand attention. Network coverage in this part of Alaska is patchy, with vast distances between stations and some gaps in real-time data. Even so, the anomalies were consistent enough to draw attention from senior seismologists. The precursor window, days to weeks before the main shock, was unusually active, with tremor energy sometimes doubling the seasonal background level. Some stations closer to the epicenter reported microseismic bursts that, in hindsight, clustered along a corridor now recognized as the rupture zone. For the team at the Earthquake Center, these signals raised urgent questions. Were they a warning of mounting stress at depth, or just noise in an already restless region? Without denser instrumentation, the true extent of the anomaly remained uncertain. the need for confirmation grew. This was an urgent problem for scientists trying to understand what was building below. Remote sensing, satellite interferometry, and global positioning system data offered a way to check for surface deformation that might corroborate the deep tremor. Satellites could provide the wider view that ground networks could not. As the main shock struck, the search for answers shifted from the ground to orbit, where satellites could scan for any sign that the Earth itself had flexed in the days leading up to Alaska's largest quake in 4 years. Orbital sensors began collecting data over south-central Alaska within hours of the earthquake. Sentinel-1, part of the European Space Agency's Copernicus program, passed over the region on a regular 12-day cycle, capturing radar images both before and after the event. By comparing these pairs, scientists generated interferograms, colorful maps that translate tiny ground shifts into visible patterns. The November 27th interferogram revealed a subtle but coherent signal northwest of Anchorage, with line-of-sight displacement peaking near the epicenter. Most of the deformation measured just a few centimeters, well below the threshold for surface rupture, but enough to confirm that the crust had flexed in response to deep movement. UNEVICO's permanent GPS stations, scattered across the Matanuska-Susitna borough, offered a second line of evidence. Station SUSI, located closest to the epicenter, recorded a sudden offset of about 4 millimeters eastward and slightly downward within a day of the earthquake. This shift, though imperceptible to residents, matched the direction expected from slip along a west-dipping fault at depth. Other stations, ANCH in Anchorage and TAL in Talkeetna, logged smaller, barely detectable changes, reinforcing the pattern seen in the satellite data. These readings provided independent confirmation that stress had been released not just at depth, but in a way that rippled through the upper crust. To check for broader changes in underground pressure, researchers turned to the GRACE-FO satellite pair, which measures regional shifts in Earth's gravity field. While GRACE's resolution is too coarse to pinpoint individual earthquakes, monthly averages can reveal large-scale mass redistribution tied to groundwater or tectonic strain. For November, the Alaska sector showed no significant anomaly, suggesting the event's impact remained localized without triggering basin-wide shifts in water or crustal mass. Each dataset has its limits. INSAR can be plagued by atmospheric noise or snow cover, GPS stations are sparse in remote valleys, and GRACE cannot resolve features smaller than about 300 kilometers. But taken together, these independent measurements painted a consistent picture. The ground had moved, subtly but measurably, in the days surrounding Alaska's strongest earthquake in 4 years. For scientists, these signals offered a rare glimpse into the hidden mechanics of an active subduction zone, setting the stage for deeper structural analysis. Alaska's seismic underworld is anything but simple. The Alaska Division of Geological and Geophysical Surveys maintains a sprawling map of faults, but beneath the surface, the real picture is far more tangled. The main megathrust boundary, where the Pacific Plate dives beneath North America, is only part of the story. Branching away from it, hidden splay faults, thin fractures slicing through the crust, lie mostly unmapped, some only hinted at by faint lineations in satellite deformation data and sparse field surveys. These structures do not always show their hand until a quake like this one passes stress across the network. After the November earthquake, geologists pored over new interferogram overlays, searching for patterns that did not quite fit the known faults. Several subtle lineations, running northwest to southeast across the Susitna Basin, appeared in the deformation field. These were not traced in earlier hazard maps. Some cut across glacial deposits, others paralleled old river channels, but all shared a faint signature of recent movement. The Alaska Earthquake Center flagged these as likely splay faults, secondary fractures that can slip when stress is transferred from the deeper megathrust or during slow slip episodes. The difference between the main interface and these splays is critical. The megathrust is capable of producing magnitude 8 or 9 earthquakes, but splay faults, though smaller, can reactivate suddenly and close to the surface. In 1964, several splays ruptured alongside the main event, amplifying ground shaking and producing unexpected landslides. Today, The concern is that stress released at depth by the recent quake may have migrated into these shallower faults, raising the risk of aftershocks or even triggering independent ruptures. State Geological Survey experts now face a puzzle. Without dense instrumentation, it is hard to know which faults have quietly slipped and which are still locked, waiting. The new deformation signatures demand an urgent update to hazard models, and they reinforce the need for targeted stress transfer simulations. Pinpointing where stress has moved could mean the difference between routine monitoring and anticipating the next surprise beneath Alaska's feet. Forecasting aftershocks in Alaska relies on more than just gut feeling. It is a numbers game rooted in physics. In university labs and federal agencies, geophysicists ran Coulomb stress transfer models within hours of the November earthquake. These models take the measured slip and depth and calculate how the event redistributed stress across the network of faults. In this case, the maps showed positive stress changes, zones where the crust is now closer to failure, extending southeast toward the Susitna Basin and along several mapped splay faults. For every patch of crust that was relieved, another was primed. Statistical models, including Omori's law, predicted a classic decay in aftershock frequency, strong in the first 48 hours, then tapering off over weeks. But the real question was not just about small aftershocks. By comparing the change in Coulomb failure function, researchers estimated a 12 to 15% chance of a magnitude 5 or greater aftershock within the next month. That risk is not uniform. Areas with the highest positive change in Coulomb failure function values, especially near shallow splays, carry the most concern for secondary slip. Historical context matters. The 1964 Great Alaska Earthquake triggered a cascade of aftershocks and splay fault ruptures, some days or weeks after the main event. In 1999, a magnitude 7 quake northwest of Anchorage produced a similar pattern, as stress migrated outward and ignited faults that had not moved in decades. The current models echo those patterns, translating the invisible push and pull of tectonic plates into a probabilistic map of risk. For researchers, these numbers are more than abstractions. They are the best guide for where to watch next. At the National Tsunami Warning Center in Palmer, Alaska, analysts reviewed the earthquake's parameters within minutes of the first seismic alert. Their official bulletin said, "No tsunami warning. Advisory, watch, or threat is in effect." The magnitude and depth, combined with the inland epicenter, meant ocean displacement was unlikely. Even so, the center's protocols require careful scrutiny, not just for classic seafloor uplift, but for the risk of submarine landslides that can generate local tsunamis. In this case, modeling showed no evidence of significant underwater slope failure, and tide gauges along the Cook Inlet and the Gulf of Alaska remained steady throughout the morning. Attention also turned to the Alaska Volcano Observatory, where scientists monitor more than 40 active volcanoes along the Aleutian Arc. The recent quake fell within the monitoring radius for several prominent peaks, including Cleveland Volcano, which has a history of sudden unrest. Following the event, the Alaska Volcano Observatory, AVO, maintained Cleveland at its standard yellow watch level, indicating normal background activity with no signs of escalation. Seismic sensors around Cleveland and neighboring volcanoes showed only routine micro-earthquakes, no harmonic tremor, no unusual gas emissions, and no thermal anomalies detected by satellite. Both agencies emphasized that while the current threat level remained low, conditions could change if aftershocks migrated closer to the coast or if deeper slip triggered shifts in volcanic plumbing. For now, the all clear from NOAA and AVO offered reassurance. But their watch lists remain active, ready to escalate alerts if new data, whether a sudden drop on a tide gauge or a spike in volcanic tremor, demands rapid action. Critical infrastructure in south-central Alaska carries a silent vulnerability. Ports along Cook Inlet, like Anchorage's main cargo terminal, handle more than 90% of the state's incoming goods. These docks rest on fill and soft sediments, materials prone to shaking and liquefaction when a strong quake hits. Water mains, power substations, and telecommunication lines cross the same unstable ground. In recent years, the Alaska Division of Homeland Security has flagged several of these facilities for urgent retrofitting, but funding and logistics have left gaps. Early warning systems, while improving, still leave some rural communities outside their coverage zones. Emergency planners urge residents to keep a 2-week supply of food, water, and medicine, and to know evacuation routes by heart. Hospitals in Anchorage and Wasilla have reviewed backup generator protocols, but smaller clinics farther north may face delays if roads or bridges are damaged. The state's official checklist includes securing heavy furniture, preparing go bags, and designating family meeting spots. Each of these steps, simple as they sound, can mean the difference between chaos and safety when the next earthquake arrives. The Alaska Division of Homeland Security reminds all residents that preparedness is not just a personal responsibility, but a community shield. Scientists reviewing the November 27th earthquake weigh the evidence with caution and clarity. The seismic, satellite, and historical data suggest that Alaska's tectonic system remains restless but not unpredictable. The probability of a magnitude 5 or larger aftershock in the next month is between 12 and 15%, highest near shallow splay faults where stress has increased. No tsunami threat has been identified, and volcanic activity remains at normal background levels. Still, experience shows that even moderate earthquakes can transfer stress, sometimes triggering aftershocks or awakening hidden faults days or weeks later. For residents and emergency planners, vigilance is the message, especially in regions where hazard maps show positive stress changes or where critical infrastructure sits on soft ground. The Alaska Earthquake Center, the United States Geological Survey, and the National Oceanic and Atmospheric Administration Tsunami Warning Center continue to provide real-time updates through their official channels. Alert levels will rise only if new seismic swarms, unusual ground deformation, or rapid changes in volcanic signals are detected. Until then, the outlook is measured. The risk is real, but the science points to watchfulness, not alarm. Staying informed through official bulletins is the best defense as Alaska's seismic story continues to unfold. Today, Alaska's seismic sensors register tremors that scientists still struggle to explain. With over 11% of the world's earthquakes striking this region, uncertainty isn't just academic, it's urgent. What happens beneath Alaska's crust can ripple far beyond its borders. The ground may seem steady, but the next shift could rewrite what we know about risk. Stay alert and let us know your take in the comments below.